One of the simplest operations in an execution plan is a scan operation. This is basically the process of accessing each row in a table. We can also scan indexes, which are a special kind of table. Scanning is a linear operation, moving from one row to the next and performing some operation like applying a filter to implement a where clause. Now, scanning is simple. The database fetches data blocks from persistent storage or a cache, applies a filter, a join, or some other operation on the row, and then moves on to the next. The time it takes to finish the scan is based on the number of rows in the table. Now, I should point out that data in rows is not always stored together. Columnar-based storage is used in data warehouses and analytical databases. This can make filtering based on the value of a single or a small number of columns quite efficient when working with large tables. Tuning analytical queries for columnar data stores is different from the process for tuning row-oriented transaction processing systems, which is what we are focused on. From now on, we'll assume row data is stored together unless I mention otherwise. Scanning is often the most efficient way to work with small tables. It can even be an efficient way to work with large tables if there are few queries or the queries against the table operate on most rows in the table. Scanning large tables repeatedly, however, is inefficient. Scanning all rows in a table is called a full table scan. If you see a full table scan in a query execution plan, it's worth looking into why a full table scan was chosen and seeing if there isn't a more efficient way to retrieve the data. Creating indexes is a good way to avoid full table scans and make execution plans more efficient. Indexes are ordered subsets of data in a table, and they're ordered in such a way that it makes it efficient to look up a row by a particular value. As a general rule, relational databases do not store table data in sorted order. Now, there are some exceptions to this, but typically an entry in an index contains the data value that is the basis for the index and a pointer to the location of that corresponding row. If your where clause references the index value, you can use the index to find rows that meet the criteria rather than scanning the entire table. Index data, however, does have a structure that lends itself to ordering. Trees are widely used to store indexes. Now, databases offer different kinds of indexes. Some commonly used index types are balanced trees, or B trees, which are used for equality and range queries, hash indexes, which are used for equality operations, bitmap indexes are efficient ways of performing set operations, and some databases like Postgres provide specialized indexes for particular data types like geospatial data.